welcome everybody again to this meeting today. We have called it walkthrough. We would like to guide you a bit through our tools and services which we as Platform Material Digital like to make available for the Material Digital community. This walkthrough will consist of several parts. The first part is an introduction into what we call workflow solutions. Let me start with a look on the agenda, which I would like to use also to speak a bit about expectations, expectation management here for our joint time today. So we have decided to really separate our walkthrough into three different parts. We would like to start with the first part, which we called Introduction into Workflows, where we speak a bit about basic concepts. We would like to convey our view on what we mean by workflows. Also somehow take up the views of projects connected to Material Digital or in the framework of Material Digital. We would then speak a bit about what the focus area workflows within Platform Material Digital is doing, but as I said, also what is the input from the different Material Digital projects. And we would like to end this part and emphasize in particular on this part also the role of semantic interoperability of workflows. And this first part is really intended for colleagues like PIs, principal investigators, colleagues from industry, colleagues who have not yet been in deep contact with our workflows activities and would like to get on a rather high level and a bit of an overview about what is behind this concept of workflows when we speak about workflows in Material Digital. So for those of you who have already been at several General Assembly meetings or have seen other materials from us, I would expect this is to a large extent repetition. It's intended really to speak in a way that we also don't need any kind of technical knowledge, but mainly that we are able to collect you at a high level, but we expect, of course, that you have a background in material science because that's what Material Digital is about. Then we come to a second part where we really want to speak a bit about concepts. About what kind of services we try to promote in Platform Material Digital. We will speak, of course, about our workflow management systems, which we make available for everybody in Material Digital. That's Pyron and SimStack. We will speak about the questions of interoperability. We will more specify what we mean by semantic interoperability or semantic integration. And we will end with the service, what is our Platform Material Digital workflow store. And this part is now really intended for materials researchers, which also should have, just to give you a feeling what kind of level this would be, should have some experience with also Python programming, for instance. Not being a deep developer, but at least being not shocked when seeing a few lines of code. And it's also a kind of update to those of you who have already been at other events, and we try to take up here also recent developments. The third part, which is then in the afternoon, that's really intended for colleagues who really want to deeply get involved, of colleagues who would like to in particular get involved into this Pyron workflow management system. I've put here even the name developer, but it means developer of workflows, not software developer, but those who are really try to incorporate something into Pyron. And that's then really a hands-on introduction in the different concepts, 4 specific use cases. So we, with all 3 parts, try to be use case driven and not so much conceptual driven. And so for different use cases, we guide you a bit through this workflow management system, Pyron. I indicated already that's not the only workflow management system we are supporting. There is SimStack, and we on purpose now said let's put this on yet another event. So in 1 month from now, there will be another session like the afternoon session today, where then also this hands-on explanation of concepts and SimStack will be provided. Good. With this kind of introductory words, let's start with the first part. Again, this first part is mainly a general introduction into concepts of workflows. And I start here with asking you for a bit of imagination, about dreaming. Yeah. When I see the word imagine, I think about John Lennon, imagine all the people. Okay, we don't want perhaps to address all the people. We want in the first place to address companies. And you could imagine that a company could analyze data of a device without hiring an expert. That would be a dream. What do I mean by this? Imagine, yeah, that's company, and the company has for atom probe tomography data. That's a fancy technique to get atomically resolved information about what is the microstructure of a material. But this is a fancy equipment, good to have. Buying it costs some money, but running it is probably even more expensive. Because you need expertise to know how to handle all the data which are provided by the machine. The other institutes who do this, for instance, from the academic world, Max Planck Institutes or others, do this as their daily business. They are experts on this. They know how to run this machine, and they can develop protocols how to process the data which you get from such kind of equipment. And how nice would it be if we could use this kind of protocols, how I need to transform data in order to get a meaningful conclusion from what the device provides me, and just run this protocol then on my own machine. And in this way, one has really added value from using workflow environments. Imagine all the companies could systematically extend a knowledge graph for the materials system of their interest. Extend a knowledge graph means we speak about structured data, and we speak often about semantically structured data. We speak about knowledge graphs as a way of representing data. But it's nice to have the data, but we would also like to have the processes how to get to the data. And if we have these kind of protocols, then we could run similar protocols in different vendors or different stakeholders, and we could, instead of sharing all the raw data, we could collect the relevant aggregated data. So from such kind of atom probe tomography measurement, a typical parameter would be an order parameter of chemical elements in my material. How does iron and manganese order locally in my steel, for instance? And I would like to make such kind of large scale study over different steels and data sets, because I have protocols which allow me to fill my knowledge graph, and that's at the end here represented by a table with this kind of highly valuable results. Workflows are the solution for this. Imagine all the technicians could perform automated round robins over different labs and methods. So that's also a typical scenario. I've here from one of our projects where I am involved, is shown here in a microstructure of advanced high-strength steel, high manganese steel, and you have retained austenite. And it's really important to know what is your amount of retained austenite. And then there are different methods available. You can do it with X-ray diffraction, you can do it with magnetic measurements. And the problem is if you have collaborative projects, and as I said, I am involved in some of them, then every lab is doing it in a different way. So for instance, even if you think about X-ray, then it's the question, do you measure in rolling direction perpendicular? Do you average in which way over different rolling directions? Just to mention one example, how different labs can do a seemingly simple experiment in different ways, and round-robin tests are designed for this. And how nice would it be if this kind of round-robin tests would be optimized, that we have the different process protocols in an optimized way available, and in this way have a comparability of results. So the amount of retained austenite is the same semantic information, but there are different protocols to get to this. And we would like to make sure that the final result is comparable. And that is only possible if we know the provenance of how these data have been obtained. So it's always a combination of having semantically structured data together with the workflows, which give us the information, where do the data come from? Imagine all of the theoreticians to come now to theoreticians could combine software tools from different communities to analyze materials. Typical example, multi-scale challenges. You want to understand the crash performance of some high manganese steel. And you have, on the other hand, some tools which allow you to have atomistic understanding of the arrangement of atoms in certain lattice structures. How do I bring these words together? Multi-scale simulations is the keyword. So for describing this kind of crash performance, there are crystal plasticity codes. Damask is one of them, which gives you the hardening as a function of strain for different temperatures. And then there are the atomistic tools. We have these quantum mechanical codes, WASP is an example. And you need to bring these worlds together. These are very independent communities which have no idea of how their respective tools working. In my group of DFT colleagues, we have little experience of how to run an FEM solver or a crystal plasticity code, and vice versa. But if we have an environment which allows us to combine these tools without that I need this technical expertise for all the codes, how much would I gain? Or how much would I gain if I could modify a simulation step without running all this full simulation again? So what happens if something changes? The basic kind of concepts are the same, but for instance, I add here now carbon, slight change of chemistry. Not everything is changing, and I would like only to redo those parts which are now affected by this change. I would save a lot of time. Or what would it be nice when I as a theoretician could run many simulations over a large parameter space? I come with another example here from steels. Zinc in steels gives rise to liquid metal embrittlement, and this happens at grain boundaries. So there's an enrichment of zinc at grain boundaries. You would like to investigate this also theoretically. You would like to know how easily can a zinc atom segregate to a grain boundary. You can do this for different magnetic configurations. But then you would like to know, does zinc here interplay with other elements? I would like to understand all other elements of the periodic table to make some design. I would like to be able to make high throughput screening in order to learn something about trends and then to be able perhaps to cure my problem of liquid metal embrittlement. Imagine all the scientists could steer our lab environments based on simulations results with an LLM. I think I cannot give a presentation nowadays without mentioning at least once LLM, but I keep it short. But there's at least one project. There are several projects in Material Digital where LLMs play a central role, and the vision is we are still far from having achieved this, that an LLM allows us to steer at the end materials design. For instance, here that's the project class agent, and so we would like the glass production characterization, that this is guided at least by an LLM, and you would like to enrich this guidance by simulations, as it's shown here, MD simulations. And so you need to bring again a completely different concepts together in one environment, and LLM may help you to guide you through this complexity. Imagine all the scientists, and now I'm again very general, could even say all the people, could combine all of this through Material Digital, bring all these different things together into one environment. How nice would this be? With this kind of imagination, I would like to hand over to my colleague.
Okay, so I will try to go back a little bit and say where we are coming from. So we are mostly groups in theoretical simulations. And why are we doing all these workflow things? We started out in a group that does multi-scale simulations. So basically, we try to do this in organic electronics. We have effects on different scales. So most of the things that are happening in organic electrons happen at the electronic scale in a single molecule. But in the end, what you are interested in is basically how would this behave in a device. So you go from the small molecule to all the way up to a full device, and you kind of have to bridge those scales. How this is done, if you do it in a simulation, basically, you start with a single molecule parameterization, do geometry optimization, and with customized force fields, and then you do generation of atomistic morphologies. There you have molecules premised on quantum mechanical level, and you do simulation example of physical vapor deposition. And then you do the calculation of charge hopping rates in full quantum mechanical electronic structure. And then ideally you do the simulation of the device. Okay, so basically you have all these scales, and these are 4 different tools you need. And the way this is typically done, or has been done often, is that you have for each a very specialized software and one expert who is doing this. Often you need HPC resources to do the calculations because they are quite intensive. And then you have to transfer the files to the next guy and do the simulation. So this is often done in a scientific group, and there you face a lot of challenges if you have these kind of software tools. So if you have new group members, of course, you have to train them, and task for them is often to, for example, reproduce a given result, apply it to another data set, or improve a given method, and then, or maybe even develop a new method. But in order to be able to do this, of course, the new employees have to know how to use the compute resources. They have to know how to use the software, and ideally, they should be able to do some scripting and programming in order to kind of do this efficiently and also adjust the code and all the different methods. But this makes it very challenging to reproduce because there are so many steps that can go wrong and which are often poorly documented. So, I mean, there has been this big study in 2016, how hard it is to reproduce certain experiments, not only those from others, but only the own results, that it's difficult to reproduce what you've done. And this holds true even for simulation. So if people try to think back what they did for simulating, the process is often you do something, you change a little bit, and then you keep going without really documenting this, and it's getting really hard to basically capture what you really did. And also, if you read the method section of some papers, there's a lot of information actually missing when you try to do what they say they are doing. The next step is, of course, scalability. So sometimes it takes quite some time to do this for one system, but the possibilities of trying molecules you might want to use are basically very high. And then you want to scale this and test a lot of systems. And suddenly you have to do manual tasks. They don't really scale. And also the resources you have might be limited. So there's, of course, always a trade-off. if you want to spend a lot of time with automatization, it only takes some time before it really pays off to do this. But if you want to do 1,000 molecules, you just have to automate at some point. Another challenge is, of course, the competence train in these academic settings. So we usually get highly trained employees. They program their stuff and produce highly specialized tools, but which are really hard to use because nobody gets paid for documentation in academic settings, but only for producing results. And then once an employee leaves, basically all the knowledge how he did stuff often leaves. And it's really hard if people wrote their thesis and then go into industry settings basically to figure out what they did and how they did it. And maintaining those tools is also almost impossible. And then you get like those lines of codes. Somebody wrote this, nobody knows what it does, but don't change it. So ideally you have something that you can reuse, but very often you also don't even know what they did in order to get the results. And the last step, which is also, of course, interoperability. So if you have multiple simulation tools, they often produce their very own specific data. And then if you want to replace it, it's getting difficult to use another tool. And so you kind of have to write adapters or parsers for all the different output formats.